Hello, everyone. Welcome to another TBS colloquium. Today we have the pleasure of having Francesca Onori as our first guest of this year. She will tell us everything about TDs. She's a postdoc at Enough Observatory and she will tell us everything about TDs. So please, Francesca, take it away.
Okay, thanks Priscilla. Hi everybody. I'm Francesca Onori, researcher at Enough Observatorio di Roma, and I will talk you about tidal disruption level, which is the main topic of my research. So I'm researching time domain astronomy, so mainly on transient, regular transient, and also gravitational wave, electromagnetic counterpart of gravitational wave. And today I want to talk about tidal disruption event and how the LSST, in my opinion, will impact this kind of science. So let's start. I will start my colloquium with some introduction on the tidal disruption event, and then I will talk about some motivation which makes this particular kind of transient interesting to study and to follow. And then I will talk you how the era of service changed the science behind the tidal disruption event, given that LSST is really coming, we are there. So I was expecting to say that the others will start tomorrow, but yeah, there are some delays, but we are coming. It is coming. And then I will show you some observational properties of tidal disruption event, which could be useful in the sense of study this transit, but also for the identification of interesting candidate. And then I will show you briefly some interesting case before going to the conclusion. So let's start with the introduction. So what is a tidal disruption event? It's a transient event which happens when a star orbits too close to a supermassive black hole, and then it is destroyed by the strong tidal forces at play if they exceed the self-gravity of the star. So in this for snapshot, it is nice to see actually what happened to the star when it's approaching invisible, let's say for the observer, supermassive black holes. So when it approached the supermassive black hole and reached the distance at which the disruption happens, which is the tidal radius, the star is compressed, elongated, and then destroyed. The disruption after the disruption, part of the stellar debris start a circularization phase, which ends with the formation of a new accretion disk around the supermassive black hole. And part of this stellar debris is escape as unbound debris. So for us to see that the disruption event, that the radius must be outside the horizon element of the supermassive black hole. And given that this distance depends on the properties of the system, specifically on the star and on the mass of the black hole involved, this means that this limitation means that if for a disruption of a main sequence star, a supermassive black hole or low masses, so with mass less than 10 to the 8 solar masses, need to be involved. Otherwise, the star would be swallowed whole by the black hole. And it is interesting to note that if a white dwarf is disrupted, then an intermediate mass black hole must be necessarily involved. So during this phenomenon, what happens is that the stellar debris starts to fall back, at least the part that is bound back to the supermassive black hole, and this gives rise to an accretion-powered electromagnetic flare, which peaks in the UV optical and or in the X-rays and lasts a few months. So when we look, we see a tidal disruption event. Actually, we are witnessing the formation of a new accretion disk around dormant quiescent supermassive black hole, which otherwise would be invisible to us. So these kind of transits are interesting because they reveal a population of supermassive black hole in the low mass regime, which are sorry, I don't know Sorry. Do you hear me?
Yes, we can hear you.
Okay, just one moment. There is something that is not working here. Just one moment.
It's okay.
Wait. Okay, can you hear me?
Yes.
Yes, okay, where the airports were
Ah,
working. So, okay, so which means that this transit select a supermassive black hole population which are complementary to what we select with AGN study, and they are hosting quiescent galaxies, but this not exclude the possibility that a tidal disruption event can happen in an AGN, but let's stay strictly in the standard case for now, and they can show us accretion process on human-friendly timescale. And so far, for now, we are studying, observing this supermassive black hole in the local universe for what we can do with the facilities available today. So they are multi-wavelength sources, so their prompt emission is in the ultraviolet optical and or in the soft X-ray band. So here, not going in detail, but just to show you some different kind of signal that can be studied with different facilities. So we have the optical and ultraviolet light curve and the spectra with broad emission lines in hydrogen and helium. There are soft X-rays when they are detected, and recently ultraviolet spectra are starting to be taken, but they are also produce reverberation signal or afterglow, if you prefer, from the prompt emission when it interacts with the hosting environment. And this can be seen in the infrared, in the optical, and in the radio. So we have the mid-infrared echo or the production late time and transient ionization coronal emission line, and some computational transient emission in the radio band. And there are also multi-messenger sources being proved to be associated with some ice cube neutrino in the high energy, very high energy neutrinos. These are the most famous ones. And they are also source of gravitational wave emission detectable in the low frequency regime, which means that this kind of signal is possibly detectable by the future space-based interferometry such as LISA or LG or the lunar gravitational wave antenna. So this brings us to the motivation for study this kind of transient, because they are, as I told you, tracer of a population of supermassive black hole which are difficult to reach otherwise, so they are in low mass regime. This means that they can be used to derive the intrinsic properties of this kind of supermassive black hole, and also if we find a way to measure the black hole mass in an independent way, they can be used for test the scaling relation in the low mass regime, which is where we miss the data point the most. And there are also tools for study the physics of accretion-related phenomena and jet launching on a timescale of months to years from the beginning to the end of the process. They can be used to study the circumnuclear environment and the hosting galaxies, and also a population study of supermassive black hole complementary to AGN. Moreover, they can be used for study the history and the formation scenario of supermassive black hole, because the tidal disruption event rates and the black holes occupation fraction in various galaxies are related to the formation and evolution scenario of supermassive black hole, given that they can be a powerful tool to unveil local intermediate mass black hole. These are related to different scenarios of seeds of supermassive black hole seeds formation early in the universe, and they are also multi-messenger sources. So how the era of surveys changed the science of tidal disruption event. So as I told you, tidal disruption events are multi-messenger sources. This means that to properly study them, it is necessary to involve a variety of facilities. So now we know that a proper follow-up strategies must involve ground-based facilities, space-based facilities, and also with different cadence. It is good to cover the whole electromagnetic spectrum, both with imaging and spectra and different kind of data. But an important step is the moment in which we identify and select interesting candidates that must be classified with spectroscopic classification, because this is a crucial step which allows us to catch the interesting case and to start the follow-up strategies with the right timelines as early as possible. So this moment, these steps in the study of tidal disruption event greatly improved thanks to the available of powerful survey dedicated to the study of transient, which allow us to increase and modify the step in selection of candidates. For instance, the Pan-STARS, Assassin, PTF, the PESO, the NUT survey were really useful in the past decade. And here it's nice to see in this plot how they impact change basically the discovery rate of tidal disruption event. So if you think that we start early in the late 90s with few candidates serendipitously discovered in the X-ray band, to a more systematic selection, identification of tidal or well-known and recognized tidal disruption event as soon as this optical survey started to enter in the game. For instance, SDSS with Swift in the X-ray, Pan-STAR, Assassin, IPTF was extremely useful in this. But the very different was made by the starting of the operation of ZDF. This brought also a changing in the identification of interesting candidates, because with ZDF we start using the broker and selection criteria, automatically selection criteria with the customized alert, which allow us to recognize earlier and earlier interesting candidates and also interesting than case in tidal disruption event. And we pass from a detection rate of 2 tidal disruption events per year until at the current detection discovery rate, the detection rate of 10 tidal disruption events per year, which was a big change in a big difference in the science that then you can do with a bigger population of candidate tidal disruption event and different and more accurate strategies for studying them and follow-up. So this is particularly important because we are on the edge of the golden age, of the start of the golden age of the time domain astronomy, not only for the whole kind of powerful facilities that are coming in the near future in all the electromagnetic spectrum, and some of them are already working, but because LSST is starting the operation, and with its properties, so the very wide field, the scanning of the sky, the deep magnitude limited, the 6 filter used, and the cadence chosen will be extremely important for tidal disruption event science, because it will bring it to a new and unprecedented era. indeed, we expect a TDA detection rate of 1,000 per year with a huge number of contaminants, and we can go to deeper detection limit, which means that we can also explore the tidal disruption event space, also going towards the fainter one, the faster one, the farther, so we can finally go beyond the local universe, going to higher redshift. But this means that we need to change again completely the strategy to select, identify candidate, and we must rely now to the brokers, also not only for alerts identification, but also for the early TDA classification by using the photometric, so the light curve. So these steps is extremely important because we need to identify candidates from the huge amount of contaminants, but also be careful in not losing the interesting case. And as I anticipated, this will bring important step in the science itself. So increasing the sample for population studies of tidal disruption event and the variety of cases. So also the peculiar cases, the faint that could be connected to intermediate mass black hole, finally. The hosting galaxy, so we could study with a statistical sample if there is overabundance of tidal disruption event in some sort of hosting galaxies or no, and investigate the early times of the emission to understand which is the dominant emission mechanism. And maybe the first white dwarf tidal disruption event could be finally announced, but we know what to look for and where. So this means that the observational features are important to be able to use in the proper way the broker and the machine learning algorithm and the alert and the filtering, all these things. So let's stop for 1 second because I talk about the disruption event, but in the standard scenario, I am referring to the disruption of a main sequence star, which is the standard case and the case that we observe the most. And when we use as input for this broker, the location, the hosting galaxy, the color, the times of the rise and the decline are all referred to what we know from observational point of view, and this means the standard case. For the peculiar case, for instance, the white dwarf tidal disruption event that I told you before, we know that there are no confirmed observation, so not so strong to rely on, and so we need to rely only on theory and simulation. But what we know is that the two cases will be strongly different one to another. Referring to the main sequence tidal disruption event, these are the standard picture. I will show you a classical example of the light curve and some properties that we know are typical of this population of transient. There is some variety in the light curve, but machine learning algorithms have been proved to be able to identify, classify accurately to some percentage, depending on the tools that one want to use, accurately classify from the light curve the candidate, the interesting candidate. But in any case, you need the optical spectroscopy to unambiguously identify a tidal disruption event in the end, because the spectra look like this. This is an example of a typical tidal disruption event with the blue continuum, passive galaxies, overimposed the spectrum of quiescent galaxies with very broad emission lines in the helium or hydrogen lines. There is a variety in the spectroscopic classification, which is mapped, so we know more or less all the subclass that we expect, but the broad of the lines are a fingerprint of a tidal disruption event. It is interesting to remind that there is also the X-ray, because we are talking to accretion process with the formation of an accretion disk. So we expect X-ray. Not in this year, it has been proved that observed that not all the optically selected tidal disruption events showed X-ray flare, and in some cases the X-ray flare could be detected with some delay with respect to the peak of the optical. When it's detected, it has some properties, which is it is soft. The peak luminosity is between the 10 to the 42, 10 to the 44 ergs per second. They have extremely soft spectra, and so on. There is an exception, which is really notably, in some cases, high energy emission in the X-ray can be detected, has been detected, and it showed a non-thermal component which can be ascribed to a phase-on relativistic jet. This is one example of a jetted tidal disruption event, extremely luminous, and indeed it was a very high redshift. But this observational dichotomy between the X-ray and the optically selected tidal disruption event open many questions about the geometry of the emitting region, the dominant emission mechanism at the various stages, the presence or not of outflow. The first question is, the optical is produced by a reprocessing atmosphere which absorbed the X-rays and re-emit in the optical, or the shock or soon after the disruption of the star, the shocks between stellar debris is responsible of the optical emission, and then after we have the formation of the disk, we see the X-ray. So we don't know for now. There is this is still an open question, but there is a model, a unification model from Dye et al. In 2018, which describe the emitting region in terms and the observational properties in terms of viewing angle with respect to an obscuring reprocessing atmosphere. So if we see the tidal disruption event edge on, we have the reprocessing atmosphere and we don't see the X-ray. If we see the system face on, we see the X-ray, and if we are really face on, we should be able to see the jet, as in the case of the jetted TDE. But of course, as the observation cases of different cases of tidal disruption event are studied, we see a variety of situations which still question this point. So very briefly, because I will need probably another colloquium to talk deeply of white dwarf tidal disruption event, but I think that it is one of interesting case to take in consideration. As I told you, we rely only on theory. What we know from theory is that given that a compact star is being compressed and elongated before the disruption of the star itself, we expect an additional source of electromagnetic emission, which is produced by the compression of the white dwarf as it approaches the supermassive black hole, and this is expected to result in a transient which mimic the supernova 1A event, but it is expected to be bluer, fainter, and faster, with a particular path of evolutionary path, especially in the spectroscopic feature. Also, the disruption of the white dwarf is expected to induce a super Eddington accretion phase, which results with the launch of relativistic jet. Also, the hosting environment are different because we expect to see this kind of tidal disruption event in the environment where we expect to find intermediate mass black hole, thus the nuclei of dwarf galaxy, but also the globular cluster. So this transient could be not necessarily nuclear, but in the outskirts of some galaxies. This is a simulation, an example of simulation of how the spectra of the supernova-like event should look like. And it should start with blue featureless spectrum, and the absorption feature should develop after 14 days from the peak of the transient, and one fingerprint should be a Doppler shift of the lines, which reflect the orbital motion of the white dwarf around the intermediate mass black hole. Also, the observational properties are expected to be extremely view angle dependent. So if you see the system face on, you see also the X-ray jet. Otherwise, you see the soft component of the jet. There are some differences. But they are expected to be blue, extremely luminous, fast rising, and long lasting. So the super Eddington accretion phase should last for years. There are some, this is a brief summary of what I told you so far about the white dwarf tidal disruption event. There are possible candidates to this. One example are the jetted tidal disruption event, and the others are the fast X-ray transient. Okay, now I will pass to briefly talk you about two cases which are interesting because they happen in a peculiar hosting environment, and these are example of tidal disruption event which could be missed by broker or automatically selection of candidate if we are too strictly to the standard cases. The first case is AT17 GGE. This was a nuclear transient alerted by Atlas and Pan-STARRS, and it was in the nucleus of one galaxy that was spiral and star forming. And the classification spectrum didn't show at the beginning the typical feature of tidal disruption event, thus was not immediately classified as a tidal disruption event, but it was classified as a tidal disruption event only later on by Wang et al. In 2022 and by myself for two different reasons. Wang classified it on the basis of the detection of a echo in the NeoWISE database. I classify it as a tidal disruption event also because I follow up spectroscopically and I've seen the late time development of the typical feature of a tidal disruption event. So it was not an immediate case immediately recognized. So this the paper is very long, so I'm not going very deep, but the main topic is that it happened in a dusty and gas-rich environment. It shows an optical emission that can be explained with the shocks between the stellar debris. This is because the X-ray has been detected with a delay with respect to the optical, and soon after there is the echo in the near-infrared, which was explained with the presence of or formation after the tidal disruption event of a dusty torus or something similar to a dusty torus, because the covering factor of this torus, I call it like this, was of 20%. So it was very similar to what commonly observed in AGN. And also there was the late time development of the spectral feature, typical of tidal disruption event, and also I took for the first time the infrared spectrum of a tidal disruption event. But the most compelling finding of this work was the direct observation of the late time development of high ionization coronal emission lines. So this has been the first case in which a tidal disruption event has been directly connected to the development and the formation of transient high ionization coronal emission line. Because this is extremely important, because in the past, extreme coronal line emitting galaxies were thought to be connected to tidal disruption event, and they were thought to be the echo of past tidal disruption event that have been missed by the current survey. So in this case, we observed the formation of this structure. And there is also a second case, another TDE, which was discovered soon after, in which we observed the same phenomenon. So this can have an impact on the tidal disruption event rate if we decide to take into account also the extreme coronal line emitting galaxy, for instance. The second case is more recent, is the TDE 2022 WTN. So this is another peculiar hosting environment. It was in the ZTF. It was recognized as a supernova at the beginning because it was not nuclear. But if we look carefully, it is in the nucleus of a small galaxy in an interacting pair of galaxies. So this system, as you can see in the legacy picture field of 2022 WTN, is an interacting system that has been passed already. That was already been a first approach of the two galaxies, because you can see the detail of the interaction. So beside a number of peculiarity in the observational properties from the multi-wavelength follow-up campaign of this tidal disruption event, there are two interesting points to take into mind. First is that at some point of the spectral evolution, it shows a spectrum similar to Bowen-Florence's flare. These are nuclear transients that take place in the nuclei of AGN, so active nuclei, and they are associated with dramatic increase in the optical brightness and also in the accretion. But we still don't know exactly why this happened, which is the mechanism at the base of this new transient. So given this similarity, a question came into my mind. So could it be that at least part of Bowen-Florence flare could be produced by tidal disruption event in AGN? So this is something that could be investigated with high sample of tidal disruption event, for instance. I made a toy model to explain the peculiarity observed in AT 2022 WTN with a toy model which is consistent with the full disruption of a low mass star by a black hole of 10 to the 6 solar masses. And in this case, circular regeneration phase efficiently build an accretion disk formation, and it was followed by the launch of quasi-spherical fast expanding outflow of reprocessing envelope. And And from the other side, the hosting environment has some implication in the tidal disruption event rate, because this is the second tidal disruption event observed in an interacting galaxy, pair of galaxies. This means, from rough estimates, an overrepresentation of merging galaxies hosting tidal disruption event, which could also be connected to the fact that we see an overrepresentation of tidal disruption event in post-starbus galaxies, which are the result of the merging, are thought to be the result of the merging of these two galaxies. This means an increase of TDE, tidal disruption event rate, by a factor of 10. But of course, this estimation have been done on two cases. So larger sample are needed for investigate on this part of on this topic, but it's interesting because this would be that the interaction between galaxy would increase in some the probability to scatter the stars in the nuclei and then to have tidal disruption event. So I leave you with my conclusion. I show you how tidal disruption events are important tool for study supermassive black hole from different point of view, so different aspect of supermassive black hole, and we have been witnessing to a great step in this field, mainly thanks to the wide field optical survey. ZTF made a difference, but there are still many open questions, and LSST will be a game changer, increasing the science that we can do with a disruption event, but also changing the approach that we need to use in identification and classification of candidates. So we must be ready to discriminate the candidate among the huge contaminants that we will have, but not to miss peculiar cases that could be interesting. Thank you, everybody. I'm finished.
Thank you so much. This was really, really, really interesting, amazing presentation. And we look forward to seeing how many more of these peculiar things you can find. Thank you so much.
Yeah, thank you.